Okay, so hello everyone. My name is Kara, and this is Noelle and Noah, and today we're going to be talking about spectral clustering. So in general, clustering is the task of grouping objects together so that similar objects end up in the same group, and then objects that are not similar to each other are in different groups. And so spectral clustering is a specific type of algorithm in order to do this that uses the eigenvalues and eigenvectors of a similarity graph and its Laplacian in order to cluster these objects. And we will see that spectral clustering has several different applications to any field that has to analyze data, and the one field we will specifically be talking about is unsupervised machine learning. So we're going to start our discussion by reviewing some parts of graph theory that will be useful to us later. And so for our purposes, we're going to assume that the graphs we're dealing with are both weighted and undirected. And so this means that for our weighted graphs, each edge of our graph is given a weight, and in our case, the weight will depend on how similar the vertices are to each other. And then our graphs are also undirected, which means that if two graphs are connected by an edge, they're connected in both directions. And so we can define the degree of a vertex as d equals the sum of all the edge weights coming into that vertex. And so then given a subset of vertices A, we will define an indicator vector as 1 sub A equals f1 through fn, where fi equals 1 if the vertex is in our subset, and then 0 otherwise. So given some data set, our goal is to divide our data points into these similar groups. And so we will start by creating a similarity graph, which we'll call G, where our set of data points becomes the set of vertices V, and then two vertices will be connected by an edge if they are similar. And depending on how similar they are, the edges will be given a non-negative weight Wij, and then it only equals 0 if the vertices are not similar, and then they will not have an edge. And then since we're assuming G is undirected, our Wij will be the same as our Wji. So now we have a similarity graph. Some other tools we will be using are called the degree and adjacency matrices. Our degree matrix will be one so that the entries are the degrees of our vertices going along the diagonal. And then it will be 0 elsewhere. And then our adjacency matrix, we will have the column and row indices represent each vertex. And then they will have the weight there if they are connected, and then 0 otherwise. And so we will call our degree matrix capital D and our adjacency matrix capital W. So once we have our degree and adjacency matrices, we will define a graph Laplacian, which we will calculate by L equals D minus W, so our degree minus our adjacency matrices. And our Laplacian then has several properties, so that for every eigenvector f, it exists in Rn, we know that our F transpose LF is equal to 1/2 the sum of the weights times fi minus fj squared. And then we also know that L is symmetric and positive semi-definite. The smallest eigenvalue is equal to 0, and our eigenvalues are non-negative real values. So we can prove this by taking our F transpose LF, and then using our definition of the Laplacian, D minus L, we can expand that, and then using our definitions of the degree and adjacency matrices, we can expand it again so that using some algebraic manipulation, we can get these sums, which then will equal our 1/2 sum of our weights times fi minus fj squared. And this also shows that our F transpose LF is non-negative, so it's positive semi-definite because our weights are non-negative. And then it also shows that this is symmetric because our degree and adjacency matrices are both symmetric. And then L is positive semi-definite, so our eigenvalues will have to be non-negative, and the smallest would have to be 0. So now that we have our graph Laplacian, we can normalize it. And there are two different ways that we can normalize this. The first is called the symmetrically normalized matrix, where our symmetric Laplacian is equal to d to the negative 1/2 times L times d to the negative 1/2. And the elements of this will be 1 if our I equals j and the degree of vertex I is not equal to 0. It will be negative 1 times over the square root of degree vertex I, degree vertex j, if I does not equal j, and our vertices are adjacent, and then it will be 0 otherwise. The second way to normalize it is called the random walk normalization. And so the random walk normalized Laplacian equals the inverse of our degree matrix times L. And the elements of this will be 1 if, again, I equals j and the degree is not equal to 0. And then it'll be 1 over the degree of vertex I if I does not equal j and our vertices are adjacent, and then again 0 otherwise. So similar to the unnormalized version, the normalized graph Laplacians have the property so that every eigenvector f equals f transpose L the symmetric version times f, and then 1/2 the sum of our weights, and then fi over the square root of our di minus fj over the square root dj squared. And then secondly, our lambda is an eigenvalue of the random walk normalized Laplacian if and only if it is also an eigenvalue of the symmetric normalized version with eigenvectors u and w equals d 1/2 u. And then both the symmetric and random walk normalized versions are positive semi-definite and have non-negative real eigenvalues. So the first and third properties are proved similarly to the way we proved the unnormalized version. And then our second property is proved by taking our eigenvalue equation, L symmetric times W equals the eigenvalue times W, and then multiply this by d to the negative 1/2, and we can substitute U with d to the negative 1/2 times W, and we will get the result. So once we have our Laplacian, whether unnormalized or normalized, we have the multiplicity k of our eigenvalue equal to 0, and this will be equal to the number of connected components of our similarity graph. And this comes from setting our f transpose LF equal to 0. And so if our graph is completely disconnected, then we will have all of our eigenvalues equal to 0 because all of our weights are going to be equal to 0. And so then fi and fj could be anything, and they will all correspond to 0. And then if our graph is completely connected, then we will only have one eigenvalue equal to 0. And then none of our weights can be 0, and so fi must equal fj. And so it'll be the same throughout the whole graph, and you only have one eigenvector corresponding to the eigenvalue equals 0. So we've learned how the number of eigenvalues can tell us the number of connected components, but there are also some other things that our graph eigenvalues can tell us. And assuming our graph is not completely disconnected so that they're all equal to 0, our first non-zero eigenvalue is called the spectral gap. And this gives some idea of how densely connected our graph is and how similar our points are. Because the higher this number, then more vertices are connected to each other and more of our data points are similar to all the other ones. The second eigenvalue is called the Fiedler value. And this lambda gives the approximate number of cuts you would need to make to this graph in order to separate it into two different sections. And then our eigenvalues can also tell how many likely clusters there can be. So the location of the first large gap in between your eigenvalues will tell you about approximately how many clusters that seem to be likely in your graph. So this is seen easily with an example. So if we have a Laplacian with these 8 eigenvalues, you can immediately tell that your graph is completely connected because you only have a multiplicity of 1 for your 0 eigenvalue. Your spectral gap is 1/2. Your Fiedler value is also 1/2. And then because our first large gap comes between this 1 and this 4, which are the 4th and 5th eigenvalues, that tells you that there are likely 4 clusters that this graph could be separated into. So now that we can move on to the actual spectral clustering algorithms. So we'll start with an unnormalized version. So we know how many likely clusters there could be. So suppose we want to construct k clusters. Then we construct our similarity graph with its degree and adjacency matrices, and we can construct the unnormalized Laplacian by taking degree minus the adjacency. And then we can compute the first k eigenvectors, which we'll call u1 through uk of our Laplacian, and we'll let the matrix U contain these eigenvectors as its columns. Then for I equals 1 through n, we will let y sub I correspond to the ith row of our matrix U. And then we will cluster our y using the k-means clustering algorithm into clusters C1 through CK. And this will output clusters A1 through AK for us. Now, For those who may not know, the k-means clustering algorithm works by randomly assigning centroids into our data set, and it clusters the points according to their closest centroid. And then it will reassign the location of these centroids into the mean of their clusters. And then once again, it will reassign the data points to their closest centroid and repeat this process until it converges and your centroids no longer move location. And then it will measure the variance between the centroids. And then it will go back to the beginning and repeat the entire process again until it has done this and minimized your variance. And then you will output your clustering result. So similarly to the normalized spectral clustering, or the unnormalized spectral clustering algorithm, the normalized version wants to construct k-clusters. You start with your similarity graph, compute the Laplacian, and then you find the first k eigenvectors. According to the generalized problem, Laplacian times u equals lambda du. And we will let, again, our matrix U contain our eigenvectors U through 1 through k as its columns. And then for each I, we will let y correspond to the ith row of U, cluster our y's according to the k-means clustering algorithm, and then again, it will output our clusters A1 through AK.
All right, so we've looked at the algorithms, spectral clustering algorithms. Now we want to take a look at why they work, because it sort of seems like they just got pulled out of thin air. At least it did to me when I first studied this. So we want to remind ourselves first about what our goal is with our similarity graph. We want to divide up our similarity graph in such a way that similar points end up in the same clusters and dissimilar points are not in the same cluster. Another way we can state this is by saying that edges between different groups or clusters will need to have a very low weight, and edges within the same cluster should have a very high weight. Now, one of the simplest ways to accomplish this is by solving the min-cut problem. And the metric we are trying to minimize is the sum of the weights of the edges between different groups. So for k clusters, we can denote the sum of the weights of the edges between each cluster or subset and its complement as the following right here. And Kara mentioned this earlier. It's basically just the sum of the weights of the edges between all points in this cluster and all points in that cluster. And the half is there just so we don't count edges twice. So this is the function that we want to minimize. This is great, but unfortunately it often ends up cutting just a single vertex off and isolating it from the rest of the vertices. So what I want to do then is we request that all of our clusters are not too small and preferably to be around the same size. We can add this request to our cut function in one of two ways. So the first way is ratio cut. We can divide by the size of each cluster, and in this case the size means the number of vertices in each cluster. Or we can divide by the size, meaning the volume of the cluster, which is the sum of the weights of all edges that are connected to any points inside the cluster. So this is great, and it is optimized particularly when each of the sizes or all of the sizes coincide. But even though we have solved our problem of getting similar sized clusters, we introduced another problem, because now this problem is NP hard to solve. So how we're going to go around this is by rewriting the optimization problem in terms of our Laplacian and relaxing some conditions. So I'm going to do this in detail only for k equals 2. And to start out by rewriting, we want to define a vector that holds information about each vertex in respect to which cluster it ends up. So if our vertex I is in A, we will denote the entry of our vector with this, and if it is in A complement, this will be the entry in our vector. And there will be n entries for every vertex in our set V. So then we can plug this vector into our relation that Kara showed earlier. And once we do that, we can show that this is the same thing as ratio cut. So here is the computation for that. I'm not going to go through in a lot of detail, but basically here we input in the definition of our entries. So since fi in this case would be in A, this would be our value according to the definition on the previous page. And since j would be an A complement, our definition would be this from the previous page, and then it's flipped over here. Then we can expand out the squares, factor out this term here, and then we notice over on this side, this is the definition of our cut function for A and A complement. This we can pull out the top since the size of A plus the size of A complement will just be the number of vertices in our set V times cut of A complement, and then times this. If we distribute cut over here, this is the definition of ratio cut. So we can write ratio cut as our F transpose Laplacian F. Some things we want to notice, though, about our F vector is that our F vector, if we take the dot product of F with our 1 vector, which is a vector with all entries equal to 1, it is equal to 0. So our F needs to be orthonormal to the 1 vector, and the magnitude of F is square root of n. So we can rewrite our optimization problem, minimum of ratio cut, A complement, as the minimum of F transpose LF, with the case that F is orthonormal to the 1 vector, and the magnitude is equal to the square root of n, and n is the number of vertices in V. And F is also defined as previously. So now we have our problem in terms of the Laplacian, but it's still a discrete optimization problem, and it is still NP-hard. So what we're going to do is relax the condition some. So instead of requiring F to have entries that take on only one of 2 values, we'll let the entries be equal to anything in R. And so it is quite obvious by the Rayleigh-Ritz theorem that the optimization problem solution is the eigenvector corresponding to the second smallest eigenvalue of L. I wanted to put the Rayleigh-Ritz theorem on this page, but it didn't fit, so I'll put it on the next page. So the Rayleigh-Ritz theorem says that if we have a Hermitian matrix A, its eigenvectors are the critical points or vectors of the Rayleigh quotient. This is the Rayleigh quotient right here. And its eigenvalues are its values at such critical points. So then we'll have that the maximum of the Rayleigh quotient is achieved at the eigenvector corresponding to the largest eigenvalue, and the minimum of the Rayleigh quotient is achieved when we input the eigenvector corresponding to the smallest eigenvalue of A. And then if we go back to the previous slide, you can sort of see that now. This is a Rayleigh quotient without the constant. And since, I guess you can ask, why is it the second smallest eigenvalue? I don't know if we mentioned this earlier, but our Laplacian's smallest eigenvalue is 0, and the eigenvector corresponding to lambda equals 0 is the 1 vector. So since we have the condition here that our F needs to be orthonormal to the 1 vector, we choose the second smallest eigenvalue, and thus the second smallest, or the eigenvector corresponding to the second smallest eigenvalue. All right. So we figured out how to optimize our Rayleigh quotient. And so now we need to convert back our vector F to a discrete indicator vector. And so most spectral clustering algorithms will just treat all of the entries of F as points in R, and then use k-means to cluster them into 2 groups, and then carry that clustering over to the underlying data points, since each entry corresponds to a vertex. So if our entry is in C, when we use k-means to cluster into C and C complement, then our vertex will be in A. And if our entry is in the complement of C, we'll say that our vertex is in the complement of A. And this is exactly the unnormalized spectral clustering algorithm that Kara showed earlier for the case that k equals 2. We're going to generalize this to k groups instead of just k equals 2. And so in this case, we want to define our discrete indicator matrix, which is n by k in R, as having these entries. And then a lot of math later, we'll have a trace minimization problem with the condition that H transpose H is equal to the identity. We can relax this similar to previously and let H take on any values in R. And then by another version of Rayleigh-Ritz, the solution is H containing the first k eigenvectors of our Laplacian as columns. We can use k-means on the rows of this H, similar to how we did with k equals 2, and then transfer the clustering back over to our vertices. And we can do pretty much the identical thing for n-cut. We define our discrete indicator matrix H with these entries, and then it'll result in this trace minimization, optimization minimization problem. But this time, H transpose times our degree matrix times H will have to be equal to I. We'll relax similarly, but this time substitute T, with T defined to be equal to D to the half times H. And then we'll have this problem with T transpose T equal to the identity. And then similar to before by Rayleigh-Ritz, solution T is the matrix containing the first k eigenvectors of our normalized symmetric Laplacian as columns. And then after k-means, we can cluster the rows, or we can cluster the rows using k-means and then carry that clustering over to the vertices. And this will give us a general normalized spectral clustering algorithm for k clusters, which Kara talked about earlier as well. So that's the justification for the algorithms. But there's an interesting connection with random walks that I would like to very briefly touch on. So since our last talk covered random walks, I'm not going to really talk about it at all, just use it. So we will assume, or say we have a graph that is connected and non-bipartite, and we run a random walk in the stationary distribution. We can define the probability that our next state will be in B, given two disjoint subsets of our vertices. So the probability that our next state is in B, given that our current state is in A, will be written like this. And then the relation between n-cut and this will be that n-cut of A complement is equal to the probability of A complement given A plus the probability of A given A complement. So we will show this. And so the first thing we want to observe in the proof is that we can write the probability that our current state is in A and our next state will be in B as 1 over the volume of V times the sum of the weights of the edges between all points in A and all points in B. Using this, we can write the probability that our next state is in B, given that we are currently in A, and using Bayes' theorem, or Bayes' relation, whatever it's called, as the sum of the weights of the edges between points in A and points in B divided by the volume of A. So using these two, then, we can rewrite our sum here of probabilities. And then it pretty much just follows that this is equal to the definition of n-cut. So this is nice because it gives us a neat interpretation of n-cut. When we're minimizing n-cut, we are looking for a partition of our similarity graph such that a random walk doesn't transfer between clusters often. And so it's a nice intuition to wrap up the theory section. So now we're going to be going on to the application.
Okay, so now that we know how spectral clustering works and why it works, I'm going to do about 3 examples of spectral clustering. The first example I'm going to do is just going to be kind of like a toy example, just to sort of show it work in a simple example. Basically, I take and I create a distribution of data that is basically 3 Gaussian blobs. So first I randomly distribute 30,000 points in a 10 by 10 section of the xy plane, and then I randomly select them for our data set, which ends up looking something like this. So intuitively, we can look at this, and if we use similarity as being Euclidean distance, most humans will group this into 3 clusters, right? Approximately, maybe 2 if you decide that. But what we want to do is see how well spectral clustering works on this data set. So first, I need a function that creates our Laplace or our graph, and then our Laplacian matrix, and then finds the n smallest eigenvectors and eigenvalues of it, so we can run k-means on them. So I created this function that I will go through. So first off, we need to find, how do I say this? So if we connect every point in the data set to every other point in the data set, we'll have a very dense matrix. And that will take forever to calculate any eigenvectors or eigenvalues. So we want to limit this and make a sparse graph. And so I used, I only connected each point to its k nearest neighbors. So what that means is, like, if k was 5, right, this point here would be only connected to these 5 points. And that's it, right? So to do that, I need to look up nearest neighbors. And if you naively just cycle through all the points, that will take on order of n squared time, which is awful. So I made a KD tree. So this will take a log time to look up. And then I created our graph, which takes n log n time now. And I used a Gaussian kernel for our similarity. So you put the Euclidean distance into the Gaussian kernel, and it gives a similarity that is high when the 2 points are close, and then drops off to 0 as the Euclidean distance gets larger. Then I created an unnormalized Laplacian matrix with this wonderful library. And then I found the eigenvalues, the first n, or the smallest n. So now I can find the first 10 eigenvalues of our graph after I run this function. And we note that, yes, the first eigenvalue is indeed 0. And we notice that we have 2 other eigenvalues that are relatively close to each other, and then we have a big jump. So remember, Kara said that the jump indicates that, or the location of the jump indicates how many clusters we have. And since this happens at the 3rd eigenvalue, we see that there are indeed 3 clusters as we expected. So now I just need to run k-means on the eigenvectors. So I made another function that essentially does that. So first I cut off the first eigenvector that corresponds to lambda equals 0. And then I also had to, because of round off error, you have to like do some strange things to figure out what 0 is. Then you get your first m eigenvectors corresponding to the number of clusters you want. And then you run k-means on it. So that's the k-means algorithm. And it returns our centroids of the different clusters in the set of eigenvectors. So the set of eigenvectors, if we have like m eigenvectors, we will essentially be just finding centroids in m-dimensional space. And then I used another KD tree to essentially find where each, or which centroid each point is closest to, so each vertex or its corresponding vector in the rows of the eigenvector matrix. And then I return an array with all the classes that I found. So then I cluster these, and then using this method, and then I can plot and color code the graph. And we see that it worked quite well. Here it did sort of overlap, maybe not quite like I would have done it, but we see that it did figure out that, yes, there was 3 clusters, and these are the general clusters. So this seems to work well, but like I said, this is a toy example that I just kind of made. So I'm going to go and look at the MNIST data set. So I'm sure many of you guys know about this data set, basically a bunch of handwritten digits with labels. So normally, if we're doing this, this is usually an unsupervised learning technique, so we wouldn't actually have any labels. And we'd be just feeding this into the algorithm and getting clusters. So I used labeled data sets just to sort of show you guys at the end how well it actually did. And so now we can try using spectral clustering. The issue with this is that it's hard to define the similarity metric, right? So we could try using Euclidean distance on this bit vector, right? Or this pixel vector, or whatever you want to call it. Or we could do like a dot product of some sort. But that might not actually work that well, right? So we need to sort of do some feature engineering. So what I decided to do, I decided to be lazy, and I took the first convolutional layers of the VGG16 neural network that was used or trained in an ImageNet competition back whenever. And I just created this little model that I don't train at all. I'm just using it to essentially create a feature vector for me. And I run it on the data. So you see I had to actually, since the images were too small, I had to pad them and whatnot. And it was expecting color and yeah. So then I run the model on the data. And then I reduced the dimensionality from 784 to 512. Not a lot. And if you try to run spectral clustering on 512 dimensions, that's not going to go very well. So you have to reduce the dimensionality more. So first, I used truncated singular value decomposition, so more in linear algebra, to linearly reduce the dimensionality to 100 dimensions. And then I used a nonlinear reduction algorithm called UMAP, which is similar to TSNE, if you guys know what that is, to reduce it down to 3 dimensions. And so now we have our final feature space. So now I create a function to do everything I did, and now we can look at how the feature space looks like. So I color-coded it according to like what number they are. And you see that it kind of did separate them pretty nicely. But it seems a little worrisome that spectral clustering might not know what to do here. But we'll see, right? So I find the first eigenvalues. And since this is not a connected graph, we do have several 0 eigenvalues. And it's debatable whether this is the first spectral gap or this is the first eigengap. I just chose this one because it seemed reasonable to me. So there's 5 clusters if you do that. And so I clustered it, and these are the clusters that it came up with. So actually, it did work pretty well, if you see. It sort of followed the boundaries. And if we go down, you can do like a mutual information type evaluation. If you just group, say, 5 of the, since we were having only 5 classes, if we just perfectly group 5 of the classes into one group so that we have a perfect division as far as you can do with 5, the mutual information score, which is not the mutual information, it's adjusted, is not much higher than we got with our clustering algorithm. So this seems to tell us that it worked pretty well. And if we go down and print like the amount of each class that we have in each cluster, we note that it did actually work pretty well. So class 0 had 94% 9s. Class 1 had 95% 6s. Class 2 had 97% 7s. And then class 3 had an even-ish mixture of 1s, 0s, and 4s. And class 4 had a relatively even mixture of 5, 8, 2s, and 3s. So our first attempt seemed to work pretty well. And that is not always the case. So I will show you an example where it did not work so well. Or maybe it did. So I used the CIFAR10 dataset. I don't know how you say that, but it's essentially a bunch of low-quality images of birds, horses, cars, boats, trucks, and whatnot. And so there's 10 classes. And I did the exact same thing. So I got to use the same preprocess function that I defined above, so I didn't have to rewrite everything. So I compacted the data down to 3 dimensions, and this is the state space, right? Color-coded according to, classes. And it looks like this is going to be much more difficult for our spectral clustering algorithm. So not expecting much, but let's try it anyway, right? And notice, apparently, this is not connected because this point, these points right here, I guess they're far enough away that the Gaussian kernel just sort of disconnected it from the rest of the graph. And so we have a few zero eigenvalues. And it looks like we can only really do 2 clusters if we're going to do anything. So I cluster it with 2, and I had to adjust the 0 because these zeros weren't quite 0. And this is the clustering it came up with. So, if we do our mutual information metric, we find that it is pretty awful. So, yeah, seems like it's pretty bad. But we go on and print our clusters anyway. And we notice something pretty interesting, actually. Class 0 has ships, airplanes, trucks, and automobiles in a higher proportion than the other classes, while Class 1 has frogs, dogs, cats, deers, birds, horses in higher proportion than the automobiles, trucks, airplanes, and ships. So essentially, spectral clustering kind of worked. Like, it at least differentiated that these guys are similar in some sense. I guess they're man-made or something. And the rest are not. So yeah, so these are my 3 examples. Hopefully this kind of gave you a better picture of how spectral clustering works and how you would use it. And maybe give you some intuition on the theory. So I guess it's time for questions.